Hello, welcome to this pre-recorded talk. I'm Katharina Schuh and I'm a PhD student at the University of Bonn. And I'd like to present some joint work with Nawaf Bourabe. We studied the convergence behavior of unadjusted HMC for mean field models. And let me start with introducing what is Hamiltonian Monte Carlo. So this is a Markov chain Monte Carlo method, and we want to sample here some target measure mu, which is proportional to the e to the minus some potential function u. And we use here a Markov chain Monte Carlo method often, for example, if the normalizing constant is unknown and we cannot exactly sample the measure mu. And here HMC now is a Markov chain Monte Carlo method which uses the Hamiltonian dynamics. So we do not only consider position, but we consider also now velocity. And then as the usual Hamiltonian dynamics, the change in position is given by the velocity and the change in velocity is given by minus the gradient of u. And if u would now be some, for example, quadratic potential, then if we look what the Hamiltonian dynamics does, so if we look at now the phase space here, x and v, and we start in some point x and v, then the Hamiltonian dynamics run along this green level set. And since we want now to explore the whole state space, we run our dynamics only up to some capital time t. And then we update our velocity and run then again our Hamiltonian dynamics and so on. And then for HMC, the transition step is now given by, okay, we have our duration time t and our input x, and then we output the position of the Hamiltonian dynamics after time t started in x and xi is some standard normally distributed random variable. And now there's some problem if we want now to implement this dynamics on a computer. We can in general not do this. So we need some approximation of the Hamiltonian dynamics. And here, well, we discretize now our time step, using this discretization step h. And then here we use the velocity Vallée integrator as an approximation of the Hamiltonian dynamics. Here we denoted it by q and p twiddle. And then the transition kernel of unadjusted HMC is as before for the exact HMC, but now we use the approximated Hamiltonian dynamics. And then with this, we can now define the transition kernel of exact and unadjusted HMC, while the transition from some position x to some set A is given by the probability that if we run our Hamiltonian dynamics, that we end up starting in x and xi in the set A, and xi is again standardly normally distributed. So let me shortly mention here, in this talk, we only consider the unadjusted HMC. There exists also some adjusted HMC, which are then adjusted by some metropolis step. But here in this talk, we focus only on the unadjusted HMC. And now, since we use the Hamiltonian dynamics, which has some very nice properties, the transition kernel of exact HMC now leaves our target measure mu invariant. So this equation here is satisfied. And moreover, we have also geometric ergodicity. In the following few minutes, I'd like to investigate further the contraction or convergence behavior of both exact and unadjusted HMC using a coupling approach. And since the unadjusted HMC makes some error by taking only the approximate Hamiltonian dynamics, we also need to bound the error we make. And let me start with introducing what it's the coupling here. So the coupling transition step of HMC is given, okay, we have two position x and y, and we run now two copies of the Hamiltonian dynamics. And we couple now these two copies through their initial velocities. So we couple xi and eta, and so xi and eta is a pair of random variable, both standard normally distributed, and we need to couple them in a certain way. And the same we do for the unadjusted HMC. And now how can we couple now xi and eta? Perhaps the most easiest way is to take xi equals eta, and then to hope that if we run now one step of HMC, that the two position becomes closer. And this is actually the case in certain situations, as Chen and Vampala have shown. So provided now u is strongly convex, which is encoded here in this condition, and they assumed also that u has bounded second derivatives, then they showed that we have contraction Wasserstein-2 distance, provided t is sufficiently small, which actually makes sense if you think of this picture with the level set on the phase space. Since we don't want to end up in the same position after one step, it makes sense to have some condition on time t. And but what happens now if u is non-strongly convex? Then Bourabe, Eberlin, Zimmer, they looked at a different coupling. I called it here contractive coupling. And the idea is now to sample psi and then set eta such that this condition here is satisfied, or this equation is satisfied. That actually, if you look at the free dynamics, this term would be actually exactly the position of the Hamiltonian dynamics after one step. So free dynamics if U means that U is 0. And and the idea is now to hope that after one step with this coupling, they become closer. And actually, eta cannot always be set like this, because otherwise eta would not be standard normally distributed. So we can only do this with maximal probability, and otherwise we take a reflection coupling. And with this coupling, Bouravé, Eberle, and Zimmer, they showed that provided now U satisfies the following 3 conditions. So the first condition is some technical assumption. The second one is as before, we have bounded second derivatives. And the third one is now that we are only strongly convex outside some Euclidean wall. So that means that inside now something else happens, which includes also potentials like a double wide potential. And with these conditions, they showed that if T is sufficiently small that they have contraction Wasserstein 1 distance, here they have some additional factor M in front of it. And this condition here on T is just, okay, we had this 1/4, we had this before. This part can be interpreted as some condition number. And this part here measures in some sense the non-convexity. And now there's maybe some problem if we are in a very high dimensional setting, then this R may become very large. And so M becomes large and this contraction rate would be very small. And also this condition on T would be very restricted. And this motivates us to look at certain high dimensional models and see if we can get there some better contraction result. And we looked here now at the mean field particle model. So we're considering a target measure mu, which is such that we have n particles of dimension d, and each particle has now some unary potential, and we have some pairwise interaction potential. And then this unary potential actually satisfies the same conditions as before, our potential u is satisfied. And this interaction potential just has bounded second derivatives. And with this model, we also were considering, or we adapted the coupling from before. So we are now considering some particle-wise coupling. So for each particle separately, we decided either to take for large distances a synchronous coupling, and for small distances, we took this contractive coupling by Bouravé, Eberle, and Zimmer. And with this coupling, we were able to prove contraction in Wasserstein 1 distance with respect to the distance L1 here, which is just the sum over all particles, provided now T is sufficiently small and that the interaction is not too large. And you can see now that all these, that both conditions do not depend on the number of particles. And we also showed this now for the unadjusted HMC, provided now the discretization step is sufficiently small. And how did we do this? So mainly we used this particle-wise coupling, and we used the particle-wise distance rho, which is actually equivalent to this L1 distance. And then for this distance rho, we showed contraction in one step and then used the equivalence. And then there was a nice consequence of this result, namely that there exists now a unique invariant probability measure mu twiddle for the unadjusted HMC. So, and we have convergence towards it. But actually we don't want to sample mu twiddle, but we want to sample mu. And so we need, in the next step, we need to bound the distance between mu and mu twiddle. And therefore we assumed additionally now also that V and W have bounded third derivatives, and then we could bound the distance between mu and mu twiddle by h squared times some distance times some term, which is linear in the number of particles, which actually makes sense since here we take the sum. So in this distance L1, we take the sum over all particles. And how did we show this? So we used some triangle inequality and managed to show that the distance between mu and mu twiddle actually can be bounded by the distance started in the target measure mu and doing either one HMC exact or unadjusted HMC step. And then, this part can now be bounded using the strong accuracy of HMC. And with this result, we were now able in the next step to show that now for each epsilon, we can now find an M sufficiently large and some H sufficiently small, such that the distance between the measure we obtain after M unadjusted HMC step and the target measure is bounded by epsilon. And how did we do this? Well, we used again some triangle trick and the contraction result and the strong accuracy result from the previous slides. And then finally, we were also able to say something about the ergodic average, which is some estimator to approximate some observable F. Namely, we were able to prove that if we consider some intensive observable, so an observable of this form here, which is something like in energy per particle, then we were able to show that for each epsilon, we can bound the bias between the ergodic average and the true observable by epsilon if we choose B and M sufficiently large and H sufficiently small. And in the case that we take here now an intensive observable, H, B, and M are now independent of the number of particles. And then finally, we did also some numerics. So we implemented the coupling. So we were looking at a unipotential, which is the potential of a Gaussian mixture, and we took a quadratic interaction potential and implemented the coupling for n equals 1, 10, and 100 particle. And we noticed that the average distance decreases exponentially fast, independent of the number of particles. And this now brings me to an end of the talk, and I'm happy to see you at the Stochastik Tage, and I'm happy to take questions there.